See if and I'm thankful to the organizers for a chance to come and give a talk. Yeah, I'm from Clemson University in South Carolina, and what I want to talk about is our linear acyclic networks, and I hope the reason will become clear as the talk goes along. But I want to remind you that Anna Karenina starts off that all happy families are alike, and each unhappy family is unhappy in its own way. And I suspect that's true for nuclear physics experiments motivated by astrophysics. When we were looking at the reaction rate dependencies for alpha-rich freeze-outs, we tried to distill out kind of minimum requirements for a meaningful nuclear physics experiment motivated by astrophysics. The first was, of course, first of all, you have to have an appropriate model of your nucleosynthesis process. Okay, so that's one thing. You have to have an observable from that process, which is usually an abundance result that is either known or measurable, that you can either have an astronomer's already measured it or hopefully will measure it. Then you need a dependency of the value of that observable on the value of some nuclear property. Okay, so you have to demonstrate that dependence, and that property might be a reaction rate, it might be a mass, it might be whatever nuclear property that you can measure. And then, of course, something else would be the experimental strategy for measuring that nuclear property, or at least obtaining measurable data to better calculate it. And I think that's you can come up with your own list or whatever that we thought pretty hard about that. But what it shows you also is this, it really does show you the interdisciplinary nature of this whole enterprise, right? Because you'll need somebody to the modeler to, or a theorist to give you the process. You'll need an astronomer or somebody to give you a abundance measurement. You'll need a modeler to give you demonstrate the value, the dependence on the cross section or other property, and of course the experimentalist to carry out the experimental campaign. But in all of this, I think there's this is also kind of important in two ways. Of course, you have to demonstrate the dependence, right? You have to show it somehow, but it has to be understandable, in my view. It's fine to run lots of surveys and say we run the survey and then we see, oh yeah, this reaction is important. But I think it's going to be more convincing if there is some good reason for understanding why that reaction has that dependency. So I'm not going to present a list of reactions that I'm proposing that one measure, but what I'd like to do is I'd like to present a picture of the evolution of a class of reaction networks, time evolution of a class of reaction networks that might be helpful for identifying key reactions for nucleosynthesis processes, or at least for understanding their governing role, should that be demonstrated by some other means, a reaction survey. And that class of networks are linear acyclic networks. These are linear in the sense that the rates are independent of abundances and do not change with time. Okay, so obviously I'm already limiting the nucleosynthesis to a fair degree here. And acyclic in that reactions proceed in only one direction, so that there's no cycle. Okay, so this usually means that unlike a high temperature process, we don't have the reverse reaction rates going on. Okay. So for example, here would be a network, here would be the neutron number going this way, here would be the proton number going this way, and we're saying that, well, with gamma n reactions are not important and we only have beta decays. And so we can go out, right? But once we leave, okay, so it's the opposite of the Hotel California. Once we check out, we can never come back. Once we leave, there's no path that's going to lead us back to that species. Okay, so
what do you expect to learn then?
What do I expect to learn? Well, hopefully you'll find out
In the next slides.
Yeah, hopefully. hopefully. Okay, maybe just a picture, that'll help you think about that, right? Okay, you can tell me later whether it was worth the 30 minutes or not. Okay, so where might these what processes might be modeled with these linear acyclic networks? Whoops, I didn't want to go that quite. So a radioactive decay chain, for example, in a kilonova. If we start off here, say with cerium 170. Oops, I'm sorry. I'm not going to. Be careful here. If I decay back to stability and I ask, oh, let me look at one of these species. Let's look at the erbium 167. As I decay back, of course, these are classic decay chains going back, and you see that there would be, of course, a main path, but there would be other paths that could be occurring. This is a beta decay with a delayed neutron and so forth. So it might be taking this path, but I might be taking a path up like this, with a delayed neutron, with a normal beta decay and the delayed neutron, and another delayed neutron, and then I catch up like that. So I have multiple paths that are, of course, acyclic. Okay, and obviously then changes in decay rates would change the time evolution of this, and so I'd like to see how to understand that. The S process, that's of course the same. If I keep the neutron density constant, then those rates will be constant with time, and so I will have neutron captures until as we heard yesterday, the beta decay rate becomes important, and I'll capture up and work my way up the network. But once I leave, I can't ever come back, right? So that's another example. Another example would be the gamma process. As long as the temperature was more or less constant. Here again is the neutron number, proton number plane. In the gamma process, I have disintegration reactions that first knock out the neutrons, and then a series of gamma alphas and gamma p's that take me down. And again, you can see that as long as the abundance of light particles is low, because they're being soaked up by the lighter species, then I really don't have any capture reactions that are opposing it. And so this is, again, an acyclic network that, again, if the temperature is relatively constant, will be approximately linear. So let me switch gear to the last two processes that I had on the list and look at them in a little more detail, because they may be ones that will be relevant in the future. And so I'm going to first talk about the end process, or neutron bursts, and I'm going to first talk about a little bit the Murchison meteorites, which were observed to fall locally in Australia, Murchison, Australia, in September 1969. The fireball was observed to break up into 3 fragments before crashing and actually shaking the ground. And fragments were collected over 13 square kilometers, with the largest piece being 6 kilometers, and over 100 kilograms were 7 kilograms, and over 100 kilograms were collected. And there's a piece, like that. That's a piece of the Murchison meteorite. And inside, after about a decade of chemistry procedures were developed, these things were known to be inside because of certain release experiments that were done on Murchison, and seeing anomalous isotopic abundances being released at different phases. There was the suspicion that some kind of component was inside, and for example, the Murchison meteorite had grains like these, which are about, as I said on Monday, about the size of a human blood cell inside, that were carrying isotopic anomalies, and have since been found to be condensates from stars. Pellin et al. in 1999 measured with the RIMS, resonant ionization mass spectrometry. They measured niobium abundances in 2 silicon carbide X grains, which, by virtue of the fact that they were highly enriched in calcium-44, were known to have condensed in supernovae. And they found this unusual pattern where they had enrichments in molybdenum 95 and 97. This is per mil excess relative to solar in the particular isotope. So they were enriched in 95 and 97. And for comparison, you see here a mainstream silicon carbide grain, which is a S process dominated. So it's clearly not an S process pattern. They were very excited and we're thinking that it was maybe an R process pattern, but it doesn't really fit an R process pattern either. It should have been more enriched in molybdenum 100. And so we were already working on this N process or neutron burst process, and so we were able to show that you actually naturally get excesses of 95 and 97 in a neutron burst. And what is that process? That process is it occurs in a shell of the massive star when the shock wave goes through. And you have a little bit of neon 22 and alpha around, and so you have a sudden release of neutrons up to maybe 10 to the 15 to 10 to the 17 neutrons per cubic centimeter for 10 seconds or so. And what happens is the initial molybdenum that is there all captures out rapidly, and so it's all depleted. And you have abundant you'll have abundant zirconium 90. That will then capture neutrons, and then it will of course fill up at there will be some abundance at 95 and 97, which subsequently will decay and give you the excesses in 90, 95 and 97 in molybdenum. So that seems to be the explanation. There are other proposed explanations, but this is the favored one. And since then, this idea of the neutron burst and in pre-solar supernova grains has really become an important thing, because it can be a diagnostic of lots of things, whether you had neutrons around in the environment that you where the supernova grain would have condensed. And so there's a lot of interest in the cosmochemistry community, and they like to play with neutron burst models, okay, but they don't like to run network calculation, okay, and they don't even like to run network codes that you give them. What they like, and this is no, but it's totally counter to me, they like Excel.
Sorry, who are these days?
These are cosmochemists that measure these. So they run and they work like mad on their machine to make their measurements. So they don't want to go, run and have to learn stuff. And they are impressively good at Excel. I don't fathom it, but I try not to use Excel as much as possible. But how are you going to do it? I'm for sure not going to try to program a neutron burst calculation on Excel. So what I'd like to do is I'd like to give them an analytic solution, okay? And so then they can play with their heart to their heart's content. So this would be modeled by one of these linear acyclic networks, and so I would write down, of course, an equation like this for each species. This is the rate of change with some time-like parameter. We normally would use the neutron exposure. If it's a case like the neutron burst, it's easier to use the neutron exposure, which is just the cumulative number of neutrons that have passed through a square centimeter over time, and so that grows monotonically with time. And so that's a very useful, and for S process studies, that was always crucial for with the parameter. But of course, what you do is you decrease the abundance of species I by all the reactions that take you out of species I, and then you increase the abundance by all reactions that take you in from K into I. And so it's that simple linear equation, which of course is just like in the S process or radioactive decay. And of course, then you put it all together and you get a matrix equation. And then there are very efficient matrix exponentiators, but I assure you the cosmochemists do not want to use the matrix exponentiators. I don't want to use exponentiate. I hate using, but they're good. But Okay, so you can Laplace transform the equation, the matrix equation, and then solve for the inverse, and then what you get is you get this you get these matrix elements for the Laplace transform of the matrix, inverse matrix, and each alpha, which is a rate for species K, is a rate that you can break up into being on a path. This is a path from the contribution of J to I is a path from J to I here. So this is this. So the cross section, the total cross section or total rate out of K is going to be the sum of all the channels, and then you're going to identify one that's along your path that you're interested in, and then of course you have the sum of all the other parts that are not along the path. Sorry, let me say one other thing. Then if you see, this is the Laplace transform, and this is just product here. So in fact, these are all simple poles. And so the Bromwich integral, when you invert it, is very simple, and you get oh, sorry, I've extended a little bit further. I've forgotten that I wanted to define an individual path contribution in terms of these quantities here, and then you have the geometric mean of all the cross sections along the path, and then you have the geometric mean of the total cross section along the path, and then you can define a path probability, which is the probability at each step as you take along the path that your next step is going to be along the path. Okay, so those are very simple concepts, but these are all the parameters that go in. So anyway, as I said, the poles are simple, and so the solution is to just integrate, and you get a sum of exponentials with these parameters in front. And these are the well-known Bateman equations, and that's long been known as a way of studying these. The coefficients are down here, and they're just products of these differences in cross rates or cross sections and other terms. Okay. And so that's the exact solution. Whoops. Okay. Well, that's all right. That's the exact solution, and it's been well studied in the past, but it has some shortcomings. First of all, you're adding essentially and subtracting a whole bunch of terms that are exponentials, and those terms C are products of differences of cross sections. And so it can get, when you get lots of terms, it can get really touchy, okay, for numerically. And the other thing is it really doesn't provide a whole lot of insight. It's just a bunch of exponential terms, and that's not too helpful. What the original studies did and this was in the year I was born, for heaven's sakes, Clayton and Fowler, Hull, and Zimmerman at Caltech, what they looked at these, and they found an approximate solution for the S process, which was basically kind of a Poisson-like form for it, where they effectively fit some of the moments of the solution to get something that worked pretty well, and replace the actual cross sections with a typical number of smaller cross sections of some kind of effective weight. And that was very, very nice. And here was an example case. It's actually not showing the time evolution. It's showing a snapshot of the abundances as they move up the S process chain in this case. And you can see that as time progressed, this flow of material moving up the S process chain moved up to higher Z. So this one right here, this is the earlier time, and then this is the later time here. And then you see on there their approximate solution, which does pretty well. I mean, it's okay. It gives a sense of what's going on. And it was very important for the whole development of the S process nucleosynthesis theory, because it was an easy thing that you could then integrate over exposures and so forth to get a sense of how abundances evolved in time. But it's a little too limited for our purposes, especially when we want to compare to multiple paths. So a student and I started thinking about this, and so we came up with the solution right here. This is the solution using complete symmetric homogeneous polynomials, normalized. These are normalized complete symmetric homogeneous polynomials, and it's, of course, you're replacing a finite sum of exponentials with an infinite sum, but hopefully it cuts off, right, as you go to height. Then what you can do is that you can identify these with what are known as Bell polynomials. And once you make that connection, then you can write the solution in this form right here. And so it's a form that looks, reasonable here, and then it's an exponential of a polynomial, a growing polynomial of infinite order, if you will, or a series. And these x's then are easily obtained by a recursion relation among the Bell polynomials. Okay, so that's the solution. And in fact, it's very interesting, because if every cross section or every rate along the path is the same, then what happens is all the x's here except for x1 disappear, and it just becomes kind of a Poisson-like form. Okay, and so the x's, having different x's, is kind of is showing you how different the cross sections are, how much they vary along the path. The solution, of course, is kind of touchy, because these are growing, and this is falling off. But if you're careful, and actually you recognize that if cross sections get too far out of whack, if one cross section is 1,000 times larger than kind of the minimum cross section, it's going to go into a steady state anyway, and then you can just kind of eliminate its dependence and get a good result. So if I go back to the my neutron burst, and I think of the zirconium-90 just getting a burst of neutrons and going across, what I might like to do is I might like to say, what is the contribution of zirconium-90 to zirconium-95 after some time, after some exposure or time? And that would be this curve. That's what we call right here, this G. Okay, and so of course, if there's no exposure, there's no contribution, but as it grows, then I get more zirconium-95, so more of the zirconium-90 goes to 95, and then of course at some point it goes past. Okay, and so then it goes off, and it goes here. It's going to higher mass nuclei. And then so here's actually running the network. The network is the points, and the analytic is the solution, the analytic solution. And so I can now go. Oh, okay.
So what is tau?
Yeah, tau is no. It's in inverse cross sections, because what it is the neutron exposure. So it's a convenient thing, because what happens is then the rate is a number density of neutrons times the thermal velocity times the cross section. And so what you do is you combine together the number density and thermal velocity of the neutrons with the time. And so you get what that turns into is the neutron exposure, which is the number of neutrons that have cumulatively passed through a square centimeter over your time interval. So it's a monotonic function of the time. Okay. This would look similar in actual time. It would just be something like 10 seconds or something like that.
So the density is dropping down somewhat. You don't need to know the density of the.
Well, that's included in the number density of neutrons.
Since the temperature, the thermal content is fixed.
Yes.
So it's the density.
Yeah, this is a constant temperature and constant density for sure. Yes, sorry. Yeah, I mean, that's of course the limit of this picture, of course. Okay. Okay, so we had been putting this up before, and there was a warning that something got lost, and of course it was in a way the most interesting thing, which was the set of numbers that I can now give to my cosmochemist friends to run this calculation on Excel. Okay.
So is it easier to use this formula than to run the network?
Well, I mean, once you have them, right, you can run it on your calculator, right? Yeah. Okay. Yeah. So, but the question is whether it gives you any insight. So, one thing that you can do then is you can ask yourself, what if I change a cross section? Okay, so I can change a cross section that's either or a rate, or a rate or a cross section, whatever, that's at some species along the path, and that can either be a rate that's along the path or not along the path, right? So let me take first the case that the cross section is, or the rate is not along the path, and so what ends up happening is this is the result for that derivative with respect to that, and so it's effectively like adding another copy of that species in the chain with all the same lengths. So I just double the number here of the species along here, and so obviously that's going to take longer to go through, to go from I to J, or from J to I, because I have to go through two steps. And then I have to normalize with respect to the cross section along the path, and that's down. So that's tending to decrease. Obviously, if I siphon off material away from the path, I'm going to decrease the contribution from my starting species. If I change the cross section along the path, then this is the result here. And so this is what I had before. This is adding one in, and so it's a difference between these two. And then here's the I have to, because I have to have units of 1 over the rate here. This is the result. So it's the difference between having what you had before and what you had by adding in the extra node. So if, for example, I multiply the cross section for zirconium 93 to capture a neutron by a factor of 10. The blue curve is the original one. The orange curve is the one with the enhanced cross section. And of course, what happens is that you move to the zirconium 95 faster, and also you see that it's moved up in value here. But you can also think of it this way, right? You're going to have more early, and you're going to have less late, right? Because you've moved it through faster. And that you can see is early on, you're going to have this one is going to be higher because it's easier to get there, only having to go through n steps than n plus 1. But eventually this one will be bigger because you've moved through, and so it'll be reduced. So it's very easy to calculate these and the dependence on the cross section. Okay, so that's a single chain, where a single chain would be relevant. In low metallicity stars, we know that there's possibility of this I process happening, and the I process is analogous to the S process, except the neutron density is higher, somewhere around 10 to the 14 to 17. And so here you see in the S process, you see the neutron and proton number, and you see that the abundances are preferentially right along stability. Because the capture rates are small, and it's hard to get away from that. But if you have a higher neutron density, you can push forward, and you'll get several mass units away, because the neutron capture rates will be higher because of the higher neutron density.
Can I ask a stupid question?
Yeah.
But at least the constant neutron number then can be a good approximation within a certain time, right?
Yeah, and within a certain time interval. And again, again, you also go back and maybe I'll mention it at the end, but it's also what are you trying to do, right? Are you trying to understand? Are you trying to precisely match something? Are you trying to motivate or understand even a cross-section dependence? Right? So we like to throw everything on the computer now, which is fine, but sometimes it's nice to go back and understand, and that's yeah. And so the I process, these are abundances of some element relative to iron as a function of the atomic number in scale to solar in a low metallicity star. And the point here is simply to show that an I process distribution actually fits better than say an S process or an R process distribution for these. So there's evidence that some of these low metallicity stars have an I process occurring, which means that you're going to need to, eventually be measuring neutron capture cross sections a few mass units away from stability. Okay, so here's an integrated current diagram for an I process calculation I ran, and just at a constant density and temperature, and so effectively 10 to the 15 neutrons per cubic centimeter. And you see kind of the integrated current is the total number of nuclei that went from one species to another over the course of the calculation. Okay, so you see, of course, there's a dominant path, or it seems to be a dominant path. But you go on and you say, okay, for my purposes, I was looking at zirconium-98 for no particular reason. It was just the graph looks good. If I get too many more species on here, the graph looks a little cluttered. But this one kind of looked good. So I go on and say, hey Google, what path should I take from iron 56 to zirconium-98? Okay. And so there will be obviously multiple paths, okay, and the question is which one's dominant, which one's the how many are there, and in the full network it turns out there's 7.3 times 10 to the 11 paths. Okay, so obviously I don't want to calculate all those, but the path probability will, of course, most of those paths are not important. Okay, so I can look at these I can look at these paths, I can rank them by their path probability. You see that there's some that are dominating and then you kind of fall off, but even the 1000th important path is still contributing, and so that's interesting. But you can use all the single path approximations that I used for the neutron burst to kind of start adding them up. And so here would be the contribution of iron 56 to zirconium-98 as a function of time. Now I'm using time here, and so we're talking a few days in this I process here. And so here's the contribution of the first path, and then here's 50 paths, 100 paths, 500 paths to the total, 1,000. Actually, to saturate, to agree well with the network calculation, I need to go to about 10,000 paths. Okay, and then I'm not, the 10,000 and on is not contributing very much. Okay. Okay, but if I have all the paths, I know what their rates are. I know what each contribution is. Then I just loop over each path, write down each, look at each reaction, and then add its contribution. And then I just get a list of all the reactions, okay, in the whole thing. So this is just showing all the reactions that are occurring. This is essentially their probability, or this is the percent of the paths that are of those 1,000 paths that are contributing, that are that this reaction is contributing to. And then this is a numerical contribution to the total flow up the line. And you can go further and you can just get a whole list. Okay, you can get a whole list, and you can see that now by the time we get out here, we're starting to get contributions that are only 60%, and it drops down to 30%. So these would be these would be the reactions that would be in the dominant set of paths that would be contributing to the evolution going from iron 56 to zirconium 98. And then you could run all those derivatives, path statistics on each of them and see which made sense. Okay, so we're just writing up some codes and going to release them on our website. And if they're interesting to you, right, what you're doing is you're taking, say, obviously it has to be a process modeled by a linear acyclic network. We will decompose all the paths in going from one species to another and calculate the effective rates and what reactions are involved, and then calculate their contributions. So my goal was to present a picture of the evolution of a class of reaction networks. And of course, it's turning out to be linear directed acyclic networks that may be helpful in identifying key reactions for nucleosynthesis, or at least understand their governing role. Hopefully I've done that, right? So now you're thinking that, yes, when I run a reaction network calculation and I follow the zirconium or the iron 56 up to zirconium 98, I'm running my reaction network and I'm solving it. But what I'm really doing is I'm integrating over 7 times 10 to the 11 paths. Okay. So maybe I can go and that's fine. We do that, and that's the right way to do things. But we can also now, for at least limited class of these networks, just pull them out, find each particular path, look at its particular contribution, and study the dependence from one to the other. Presumably, what's happening when you're changing a cross section, you're changing the relative importance of one path with respect to another. So just going back, I'll leave this up as my last slide. Hopefully what this will help is with this right here, understanding and actually helping you explain to somebody why an observable is dependent on a particular nuclear parameter. Okay. Feynman said that if you can't explain to a person in a bar what you're doing, you don't know what you're doing. And so this might help with that idea. Okay, thanks.
Thank you very much, Brad. It's interesting to see that you are approaching it with analytical ways to try and understand it. And maybe you can make a short statement. How does that compare to what, for example, Anush Parikh and people like that do when they do the Monte Carlo analysis of a full network?
Yeah, sure. I mean,
what's the gain in terms of?
Well, I think you get quantitative. You get an answer, right? You get an answer that this cross section will affect things by this much. You get a a distribution and a width and all of that. But at some point, are you more satisfied? I mean, the S process we saw from Sergio, we have, this branching will either make more or less of this species, right? And you can see it either goes this way or this way.
Yeah.
You can explain that. You could probably explain that to a congressman, right? But I don't think you can explain to a congressman that somebody ran a Monte Carlo calculation and make up this. So that's what I'm after, right? I'm after that. I'm after that really simple explanation. You know? And now, whether this is simple, I don't know, but people are used to. I need to go from Clemson to Atlanta, and it presents me with 3 paths. And the first one, and then the second one is 3 minutes slower, and the next one, oh, I get that. That's a path, that's a path, that's a path. And they all contribute in the nucleosynthesis network. I can actually start to have a mental picture of that. So yeah, that's I'm not saying that we do this instead of that, because obviously we're limited by having an acyclic linear network.
No, I just wanted to hear something about the comparison. It's clear that those are 2 different approaches that give you different types of insights, and I'm sure you must have compared.
Oh, well, no, we're just kind of getting going on this. So yeah, but again, it's I'm not expecting it to give you anything more superior. But
Here's a question from Carlos.
So I am confused with the motivation, because first you said that you are simplifying your network, making it linear acyclic, but it's very complicated. Only you can do it. Those guys with the Excel sheet, they cannot do it. And then you say, I am trying to give them some analytical formulas, but they are also complicated for those guys. I'm not so sure those guys will be able to implement in the Excel sheet.
oh, sure they can.
They can,
Oh, you can take.
but did you try to give them those?
Yeah, no.
And they did
understand.
it?
They understand, right? They can take they can take something to a certain power and they can take an exponential. So.
Yeah. And the other thing is that you still didn't give us any key reaction, right? You're saying about the future.
Yeah.
Now I can, and lastly, the quotation about Feynman, I think this is absolutely bullshit, because he gave an interview with the reporter and he got upset that the reporter asked him a simple question and said, how can I explain you that? You don't know anything. You expect me to explain. This is in YouTube.
Yes, no,
So-
but that was on causality.
Yes, but you see that people make these quotes. Einstein said that. Lionel Messi said that. And then it is as if they say something we have to follow.
Of
This is all
course.
bullshit, man.
You could
Even Feynman, he would make quotes that he would not follow, okay?
okay. I think if you need to go and talk to your congressman about something, you're gonna need something simple, right?
Right.
So maybe I can say that, right?
But
Like I
if you
said-
show this formula, you still not understand. It doesn't understand anything.
If he shows you the formula, but if I say, okay, if I'm looking at the contribution of iron 56 to zirconium 98, it's like I'm asking Google to go from here to here, and I've got all these paths and they all add together. And then if I change this cross section, what's happening is, oh, there's a traffic jam here, and so I have to go by this path instead,
Right.
and I'm gonna arrive 5 minutes later. Oh, that happens to me all the time, right? I get it, and then I understand the process.
There was a brilliant nuclear physicist, Steve Cooney.
Yeah.
He went-
Alive.
And he went to New York. He went to New York to solve the traffic problem in New York. You know that, right? He became the chief operator of New York traffic. And he failed.
Well,
Well-
because you assume that. You
It's
assume that
not-
people act rationally, I'm sure that's.
Well, I'm actually a little bit skeptic about this congressman argument, because I think we are here at a different stage. We are not at the B squared FH stage. We want to understand the I process and
Oh,
the
of
neutron
course.
star burst,
course.
neutron burst.
Of course, no, I mean, I
So-
understand that. I understand that, and you can take it or leave it, but.
Mhm,
But if you, it's a nice way to understand effectively branching in a network.
mhm.
And-
Can your approach go all the way to the R process? Is it extending over the full continuum of the neutron intensities that we might find?
Well, no, because once you start talking about the R process, you're gonna have reverse reactions.
Mhm,
And then you don't have you don't have an acyclic graph.
mhm.
I have some ideas on how to include, kind of extend it to,
Mhm.
but then you're gonna get, kind of these things on top of other things, and then it's almost, is it worth it?
I'm just worried if I think of a massive star envelope like what Sandro Kirfi showed us earlier, then in these convective zones you will find a range of intensities of neutron exposure.
Yeah,
So-
okay, so, well, I mean, to the extent that you can, I mean. You would have, in my picture, what you would have is you would have this range of conditions, you would have a neutron burst everywhere, and then, of course, you have multiple species contributing to a given species. So you're gonna have to take all of those different path ideas,
Mhm.
add them up within that zone from each different starting point.
And then
And
you
then
would do
go
a
to
weighted
each
sum.
zone, and so, yeah, I've just kind of completely pulled it apart.
Mhm,
You know,
Yeah.
in my approximation,
mhm.
but it's gonna be up to you to kind
show
of put
the
it back
elementary
together,
steps.
if that's worth it to you, yeah.
So it is interesting that you mentioned the Friedman equations, which we use in nuclear decay, the chain.
Yeah.
But what do they help in this?
Why do they help the
How
Bateman?
would they help in this solution of this pass? How would they help you? To
Well,
understand?
they're the same solution. It's just I've represented them differently. Yeah.
They are,
Yeah, they're the same
so we
solution.
have the exponential decays, then
Yeah.
you don't really have exponential decays.
Yeah, you have something that looks like a Poisson function effectively.
Hmm.
Which is, of
Okay.
course, if you solve the Bateman equations, that's what they will do. All we've essentially done is taken the Bateman equations, expanded it all out, and then refactored it into a different form.
Let's have a final question from Aldo.
Did I understand well that your method works better when you have a large number of neutrons?
No, it's really not dependent on that. It's the concern is if you have a lot of neutrons, then you're probably in an environment where you have reverse reactions, which then, kind of invalidate the assumptions that underlying the method.
So that's how
Quadratic term would not be important at some point. For example, quadratic term.
Oh, yeah, well, if the network becomes nonlinear, of course, this also becomes not relevant, yeah. So you have to assume that in this case, that the neutrons are constant. But again, right, you might want to be using this as a way to explain something. You may not say, okay, I've run the massive calculations, but now I can kind of explain it more easily to somebody.
Yeah, the concern always is that you might be explaining what you expect because you do the kind of analysis that you do, but you don't know how close that is to reality or how far that is from reality. Because you're taking an approximation and you're explaining the result of that approximation.
Oh, well, yeah. I mean,
But where's the validity check?
Yeah, well, that would presumably come from the model and the extent to which the whatever the conditions were, satisfy the approximation.
I think we have to come to an end of this, that we can discuss more in the coffee break.